Okay, welcome back. So this session is about measurements at different layers. So we have a quite diverse program lined up. So the first talk will be by John Heidemann from USC ISI. And it will be about routing and stability of Anycast. So,
okay.
Process goes.
So thank you. So I'm from USC, University of Southern California. This is joint work with Lan Wei, who's a PhD student there. She unfortunately can't be here due to visa issues, so you're stuck with me. Just a second. So the question here is, does Anycast work? And we know that Anycast has got to work because it's so widely used, right? It's used by almost all of the routes. It's used by a number of commercial content delivery networks that ship terabits of traffic every day and get paid tons of money to do it. So clearly Anycast works. But the question of this talk is, does it always work? And in particular, there's always been this fear with Anycast because it's always based on BGP. Well, what happens if BGP switches the routes while you're changing your data? So that's the question we're trying to look at. And in particular, clearly it works for most people most of the time. We're particularly interested in, does it fail for a few people a lot of the time? So that's the question we have. So what is Anycast? To cover a little bit of background briefly, in Anycast you have different sites around the world. You use BGP to associate you with hopefully a nearby site, right? So whatever BGP thinks is the closest site is where your traffic is routed. Other people in other parts of the world get routed to other sites, hopefully the closest site, although not always because it's a lot messier than this, and other people in other places. And we end up dividing the world into catchments, right? Zones that go to each site. Although, as I said, they're often messier than these. So the question we have is about Anycast stability. If you have somebody who's sitting on the edge of a catchment, is it possible that they flip back and forth from one side to the other over time? And if so, what does that mean about their ability to use this Anycast service? Okay. So the contribution of this work is to do the first study of this question using public data independent of an Anycast operator. There have been a couple of studies before that have been by operators that found very little problem. And our takeaway is consistent with what they found, right? Anycast is very, very stable. But the caveat we have is it's not 100% stable, and we'll quantify that. And the other thing I'll show is that it actually seems to not be stable for a few people persistently, which is not exactly what you'd like to see. So how do we do this? Well, we're doing a big measurement. We use RIPE Atlas. So we used about 9,200 probes, vantage points around the world. You can see them plotted on the right, their locations. Our targets are the root DNS servers. So at this time of the 13 routes, 11 were Anycast, so we study those 11, and you can see their locations around the world. There's more than 500 sites at the time of our study. The probe mechanism is to use chaos probes. So if you do a chaos type DNS query on hostname.bind, that returns an identifier for the server that you contact. And we can decode those identifiers to indicate which site you're looking at. And so we're looking, the exact encoding is operator specific, but it's reasonably well known, and we look for those kinds of, we're able to decode those to figure out which site we're looking at. So which Anycast site are you going to? We have 2 data sets, each is a week long, and they're taken 8 months apart. And we'll talk about how frequently probe later. And the thing we're looking for is what we call Anycast flips. So if you're probing and you get a site like LAX at one time and then you switch to a different site like MIA, that would mean you've changed routing to a different site. If you're at B1 LAX and you switch to B2 LAX, we don't consider that a flip. Okay, so that's the methodology. Okay, so briefly about prior work. So there have been 2 studies we're aware of by Anycast providers, both of which don't give any numbers, but say, yeah, it's very stable. And we agree with those. But you have to be careful interpreting that. One, it's done by the providers. But more importantly, if you're looking at your own data for your own clients, of course, Anycast works for those clients, because if it didn't work for those clients, they wouldn't be your clients. So you have to be careful interpreting that kind of data. And there is one big limitation about our study, which is we are studying using UDP. And even though we have a lot of combinations, about 90,000 combinations, we were unable to directly test TCP connections at the time we did this study. And that actually just recently got resolved, so hopefully in the next few weeks we'll be able to revisit that. Okay, so overall the results are, as I've kind of hinted, there is a small amount of instability. It's very small, but if you're in one of these unstable sites, if you're one of these unstable vantage points, you're going to be unstable typically for a fair amount of time. And I'll quantify that in a bit. And we think these flips for these unstable sites are very frequent, like perhaps every packet. And I'll show you why I think that's true. Okay, so let's get started on the data. So this is what we call a strip chart. So this is time on this x-axis and space on the y-axis. Each row is a different right atlas vantage point. Each column is a measurement every 4 minutes. And the colors indicate which site you go to. And the exact mapping doesn't matter, but different colors are different locations, different sites. So the first thing you should take away is things are very stable, right? The graph is mostly solid colors. And this is a subset of it, so there's many more vantage points. But you can see there's some dashed lines in here, and those are things we'd like to look at a little bit more carefully. So let's zoom in on just this top corner, 20 hours and 50 vantage points. And what you can see are, one thing that we see is this kind of a band, right? A vertical band where a bunch of people switch one site and maybe 5 hours later switch back. So that's Anycast doing exactly what you'd like. There must have been some problem or some routing change, switched for a while, then it switched back. Everybody was happy. It was always getting requests through. But then we see there's also things like these two rows up here, which seem to be flipping back and forth fairly frequently. And that's a little concerning because they don't seem to be very stable. They seem to be switching. And so if you had a TCP connection that was going to the yellow site, and then the routing switches to the gray site, your TCP connection would break, and you'd have to start over. And in fact, we even see a few sites where they're flipping between 3 sites. Okay, so those are the kinds of instability that we're looking for. And we're concerned about them because they could be a problem. Okay, so that's a qualitative view of a bunch of the raw data. So to quantify how frequently this is, we look at a CDF of how long it is that you spend at any given site. And if you look, so our first data set, our first week, about 1% of vantage point, root servers seem unstable, seem to be flipping back and forth in either 4 minutes or 8 minutes or less than 10 minutes. Okay? And when we repeated the experiment 6 months later, we got a similar result, about 1% unstable. And it varies a little bit across routes, and it varies a little bit across time, but a few people seem to be unstable and frequently flipping. Okay, so that might not be bad if a few people are unstable or flip frequently occasionally. But before I get to that question, the first question we ask is, well, so where is this problem? Are you flipping because I'm on a wireless link or something and it's going up and down? Or maybe I'm flipping because there's a problem at one of the routes. And so to try to get a handle on this, we ask the question, do we see, is a VP flipping, is a vantage point flipping across all the routes, or is a route flipping for all the vantage points? And so this graph on the right is a CDF of how many VP letter combinations, I'm sorry, for each VP, how many letters is it unstable for? Where unstable means flipping, what was the definition? I think less than 10 minutes. And so what we can see is most vantage points are flipping only for a few letters, like 60% for one letter and 80 or 90% for 2 or 3. So it doesn't seem like these frequent flippings are either at the VP, nor does it seem like they're at the root letter. It seems to be some property of the path between the two. It seems to happen only for specific combinations. Okay, so that helps us decide. It seems to be something in the network. So that's encouraging. The next question we want to ask is, does the problem, is it transient? Do you flip and then you stop flipping, or does it go away? And to look for persistent instability, we either took our week long of data and then split it into two and asked if you were frequently flipping in the first half, were you also frequently flipping in the second half of the week? And what we see there is it's pretty stable. If you're flipping for the beginning of the week, you're likely to be flipping for the second half of the week. And that's kind of concerning, because that means you're flipping for days and days. Your use of this service is not going to be stable for days and days. And in fact, even when we look 6 months later, 10% of people, 10 to 20% are still unstable after 6 months. Okay, so the problem, at least for the people that are flipping, is not a transient problem. So the final question is, how frequently do you flip if you're flipping? And this is an important question because, even with TCP, connections are pretty short, right? You can connect, get your web page, and quit. So if you're stable for a minute or two, that might be sufficient. So we wanted to look at how frequently you could flip. And unfortunately here, Atlas, which has done us great up till now, gets in our way a bit, because Atlas doesn't want to hurt the network, so it limits how quickly you can probe. And so we were using the standard Atlas probes, which are 4 minutes apart. We set up custom probes, which are 1 minute apart, the most frequent that it lets us take data. But 1 minute's a long time. So we did two strategies to try to get more frequent data. One is we kind of hacked Atlas. If you run concurrent measurements from the same vantage points independently, they're not synchronized, and so you can get more data than you're supposed to. Don't tell anybody about that. And the other thing is we looked at some statistics to try to judge, does it look like the data is smoothing out? So the next slide shows both of those results. So on the right, we see the data when we ran concurrent probes and got about 20 seconds. And it's messy because it's not really 20 seconds because they're independent and they can drift. But and what you should take away from this is this bottom set of points are 4 minute probes, and this top set of points are how many flips we have between each pair of 4 minute probes. The top set of points are how many flips we have between our frequent probes, about every 20 seconds. The key takeaway is, if you're able to probe faster, you see a lot more flips. So that is consistent with 4 minutes undersampling the flipping frequency. Then on the right, we see the statistical analysis. So we took our 4 minute data, which is very regular and consistent, and then backed it off 4 minutes, 8 minutes, 16 minutes, and looked at the fraction of people that are flipping. And the behavior is similar across all different time scales. So that's not definitive, but that sort of argues that regardless of which time scale you're looking at, you're seeing noisy behavior. Again, that's consistent with undersampling the actual phenomena that's going on. So this suggests that perhaps we're flipping every packet. And we can't prove that, but that's as close as we can get with measurement infrastructure that we have. And we also obviously would have taken data from our own sites where we could control measurements. But as I said earlier, flipping is very rare, and flipping is dependent on the path, the source and destination locations. So the sites that we control aren't in interesting enough locations, apparently, to see this kind of flipping. So this is the closest we could get. The final thing, so to get at why we think this is happening, there's been some prior work by different groups arguing that there are load balancers around different links, and that when traffic goes over a load balancer, if the load balancer sends it over different paths, sometimes parts of the packet change in different ways, in ways that can end up with it getting routed to different locations. So what we're seeing is consistent with that, a very few set of places going over strange links that seem to cause the traffic to diverge. So that's been discussed before in the context of traceroute and ping. We're the first people to discuss it in the context of Anycast. The other biggest concern about our study is our concern is that TCP connections might be broken. If you have a TCP connection and the routing changes in between. And we can't directly test that yet because of limitations with the version of RIPE Atlas that was existed over the last 6 months. We just checked yesterday, and it looks like a new ROM has gotten fixed out that should fix that bug. So we definitely want to rerun this result with TCP queries to prove the concept directly. When we ran it 6 months ago with the broken ROMs, TCP failed all over the place, but that's because of software bugs, not because of flipping. Or I can't distinguish between the two at least. So what to take away from this? Well, the good news is Anycast works. We have, I think, a definitive paper to argue that Anycast almost always works very well. And you shouldn't be afraid of deploying Anycast for cases where you have TCP connections because it's going to almost always work. That's good news. The bad news is for a tiny fraction of people that seem to traverse these unusual links, they may have problems, and if they have problems, they may have problems for a long time, for days or weeks. Now, there is some other good news, which is, if you recall, when we looked at VPs going to different root letters, the problem exists only for certain root letters. So if you operate an Anycast service, my advice would be operate multiple parallel Anycast services that are different, that use different sites, and one of them will probably work for some of your clients. You can guarantee service, but you don't necessarily know which one. So that's implications. Just to wrap up, the instability seems to affect about 1% of pairs. It almost always works, and we hope to confirm this result for TCP shortly. So the data is available, and that's what I had to say. So I don't know if there's questions or...
We have plenty of time for questions.
So it's for only 1% of the probes you're using.
1% of the probe target combinations, yeah.
So could you find that like probes that are affected by flipping are mainly in certain areas, or are they spread out everywhere? Is it in certain part of the...
That's a good question. I don't think, so we didn't look explicitly at that. I don't think they are, the problem doesn't seem to be specific to probe location because probes don't see flipping across all the letters. So it seems to not be about where the probe is. It seems to be about the path between the probe and the target. Now, are there particular paths that are more dangerous than others? We didn't look at that question. That's a good question. So, other.
In your graph which showed the percentage and the two things, the shape was very different between the 2 6-month periods. So while if you cut it about 10 minutes, they're kind of similar. But
so the shape, yeah, so there's more of a bump here in this one.
yeah, and it comes down a lot.
Bump over here, kind of. Yeah, I mean, our claim is there's a small percentage that are consistent. I think that's a solid claim.
Do you think there's anything interesting going on, say to the left of that, even the sort of, if you cut it 20 minutes, there's quite a different picture?
There's quite a different picture for a few letters.
Yeah.
And
is that something to do with
I
their
don't know why there are
capacity?
these steps. I mean, these steps partly come from aliasing due to the measurements. The measurements are every 4 minutes, which is why you see a bump here and here.
Okay.
Now, why that doesn't occur over here, I'm not so sure.
Right.
So those are good questions, things to look at. So, was there a question over here?
So you specifically looked at the DNS root servers. Did you investigate the Google public DNS as well? So is there any gain from using Google public DNS? So does the switching go away for these specific?
That's a great question. So I don't know if Google public DNS uses Anycast or not, but surely it must. And probably it's very widely Anycast because Google has 1,000 or more POPs. We did not look at that. That's an interesting question to look at. So yeah, I guess that's future work. So
For the root server, there is a field somewhere that tells you which instance.
Yeah.
Yeah, the hostname.bind queries tells us which instance.
Oh, Google, do you know
Google before, and we had a way to figure out the sites at the time. I don't remember how we did it at the time. I think it was hostname.bind. So I think they do that, but that's been a while. So,
So the root servers all serve what 10 to 20% of their queries over IPv6. Are you going to expand?
did we look at IPv6? That's a good question.
I think the measurement IDs that you've listed in the paper are all over v4.
I believe they're just v4. That's probably just an oversight. I'm sorry.
Sure.
Just like everybody else, I always forget v6.
But I imagine it could be unstable in different ways.
Yes, that's a good question. I'll have to. That's worth following up on. I don't anticipate the results would be significantly different, but it would be good to check. Yeah. Other questions in the back?
So is there anything about using multipath TCP over Anycast IP? Is that going to work? If you sort of
So the challenge with TCP over Anycast is if routing changes, you lose state at the other side, and so if you go to a different random place, you'll get reset. I could imagine multicast TCP, multipath TCP, so that has mechanisms to tear down and bring up state at multiple locations. However, it would not interact with BGP, so you wouldn't know when to do those things, and you wouldn't be able to, say, keep a stable connection. It's interesting. It might be interesting to try to make that work. It's not obvious that it would work straight out of the box, but maybe you could make multipath TCP work.
I guess multipath is just multiple paths, but between the same two pairs.
Yeah, I could imagine if you used a combination of unicast and anycast IPs, you could manage that state. That might be a good way to manage things. So
actually about TCP, we were looking to Anycast impact on TCP traffic on CDNs. And we were using passive measurements, not active measurements, so different kind of approach because we were looking only from a few vantage points. We basically saw very stable behavior. Over 6 months or so, we saw just 2 or 3 glitches. I mean, you can see that there is a change in the patterns on. And also the fact that it's lasting very, very short, like a couple of seconds. So in practice, it works very well, at least from our vantage point.
I mean, as I said at the start of the talk, right? The fact that there are commercially successful Anycast providers means clearly this works well the most of the time. I do think we have to be careful about the sampling bias. If you look on clients where it works, yes, it works there. I mean, our data shows it's very, very rare that it fails, and it's only certain combinations. We had to look pretty hard. It would be interesting if somebody running a commercial CDN using Anycast could look for that kind of behavior. Anyway,
the operators who are flipping, do they know about it? How they found out?
Yeah, so if you believe what we say about where the problem is, that the problem is in the middle of the network, not at the target nor at the client, the challenge is the operator that you care about is some random ISP in the middle of the network, somebody giving you transit. So it's hard to know who to notify about that. It's not the endpoints, and that's very hard. So we did not try to contact operators, and we haven't actually tried to nail down which specific links, and that would be good for future work.
The persistence of this problem seems
Yeah.
that some of them are not aware.
Yeah, and the nice thing about the persistence of the problem means you might have a couple of days to get your trouble ticket filed, as opposed to, if it's transient things are always hard to debug. Anyway.
So, sorry, I was going to ask a question. Have you actually tried to identify any common?
No, we haven't, and that's a good thing to do. We need to do that. That would be a great thing to look at.
I know you said you haven't done TCP yet, but are the UDP probes on the right paths? Can you control the source ports? Can you ensure that successive probes are effectively the same flow?
I don't think we can control the source ports, and in general,
'Cause then, yeah, if
I
you're
don't
not,
think we know the hashing algorithm used by load balancers.
So,
Well-
docketing,
I'm sorry?
can we run docketing from the right, from the?
You would have to ask the right guys.
Docketing, well, it's just essentially like a load balancer aware thing.
So-
We should talk rather than interrupt.
Yeah. So I'm stuck using the right Atlas infrastructure, which is not a bad thing because it's diverse, but
I think it's just tough to say it's a flip if you're not controlling the flow.
controlling the flows.
If you generate two flows
And-
go two
and that's
different
why-
places, it's not a flip really.
So I think we can get a good answer to that by using TCP, because
Like definition.
all load balancers that are sane, I think, would try super hard to keep TCP over the same path. And so we were very interested in rerunning our experiments with the current Atlas ROMs.
There's some good definition. There's some good instances of not saying.
Yeah, and I do want to be very careful about the limitation of this study, that we can't make hard claims about TCP breaking yet. So, okay, well, thank you.